So x is going to be the amount of rainfall, and according to what the question says, this follows a normal distribution. Like what we talked about last week, Saturday, I was saying, I was trying to remind you guys that when it comes to a normal distribution, the question must tell you that it's a normal distribution because you are not supposed to spot a normal distribution. That is different from binomial distribution. You are supposed to be able to spot the binomial distribution. So normal distribution with a mean of mu and a standard deviation of sigma, and assuming that the rainfall each day is independent of the rainfall from the other day. Why do they need to give this statement? The rainfall on one day is independent of the rainfall on the other day, because later on they talk about the mean rainfall. They talk about the mean rainfall that is chosen from 7 days. So we are talking about sample mean distribution. Mean rainfall of 7 days require us to do x1 plus x2 plus all the way until x7 divided by 7. And because we are trying to do a linear combination, whenever we do linear combination, regardless of whether you are adding x to y or you are just adding different x together, x1, x2, x3, they must all be independent of each other. They must all be independent of each other. That is why the moment when you recognize that the question is asking for a linear combination, very often they will ask you for an assumption. So the moment when you see this chance, what is that assumption? The assumption will be they are independent of each other. They are all independent of each other. So this, when it comes to our H2 math, we can just use a notation to represent this because the examiner is supposed to be able to read that. If you were to write down x bar, then x bar will be equal to the sample mean distribution, will be equal to this that you have indicated through the number that you write on the other side. And here is going to be equal to mu and sigma square over 7. Number one, please don't anyhow write down central limit theorem, because there are people, okay, very few, but I just hope none of you are doing that. But there are people who thought that they can do central limit theorem by default. There are people who thought that, hey, because central limit theorem, you may or may not know that it is a normal distribution. So since you may or may not know that it is a normal distribution, you must as well just central limit theorem all the way. Then you don't have to decide. Central limit theorem will only be getting you marks if you are actively making a decision. It's not through using central limit theorem as a default. If you are spotted by the examiner that you are trying out this, okay, you are not going to get the marks, you may even get marks minus off. So please don't anyhow quote central limit theorem, okay? In this case, we don't need it to be a central limit theorem. We don't need to apply central limit theorem because number one, because 7, the sample size is really too small. And number two, because x is already following a normal distribution, so you don't have to do an approximation. And at the same time, for this 7 here, just in case any of you are still trying to question about this 7, I told you before, you don't question about this 7, you go back and look at the derivation. Let the derivation explain to you why suddenly you have a variance divided by n, but the mean you don't need to divide by n. Because it is through a series of manipulation. You can't look at the result and then just explain based on the result. Okay? So we have this, and it's a very, very easy and standard question. It is given that 10% of the chance there is a 10% chance that the rainfall of a randomly chosen day exceeds 9.8. So from here, we know probability that x is bigger than 9.8. This is 10%, so 0.1. And as for the mean, according to what the question says, there's a 10% chance also that the mean amount of rainfall exceeds 8.2. So it is the probability that x bar is bigger than 8.2. This is equal to 0.1. We are supposed to show that sigma is equal to 2.01, correct to 2 decimal places. To me, this is a test of standardization. I don't think it is very difficult. Standardization actually goes through a process where we are supposed to take x minus away its mean. So I'll take 9.8 minus away its mean, and I'll divide by its own standard deviation. So I'll divide it by this. This is equal to 0.1. And because we are just manipulating the inequality that is within the bracket, everything that is outside the bracket will stay the same. And as for x minus mu divided by sigma, it is always going to give you, x minus mu divided by sigma will always be giving you a normal distribution with a mean of 0 and a variance of 1. It will always be, that will always happen. It can be very, very easily proven also. I don't think this is a very critical proof. The one that is meant for sample mean distribution is a more critical proof, but I can just very quickly go through that with you again. So if I were to take X as one that follows a normal distribution with mu and sigma square, we can see if I want to analyze a particular kind of combination of X, which I take X minus its own mean divided by its own standard deviation, what if we were to find the expectation? What if we were to find the variance? That means through maybe trial and error by someone, okay, we don't know who that person is. Actually probably the math history will record it. It's just that I didn't put in effort to go and find out who that person is. But our aim is just to find out, what if I were to take X minus its own mean minus its own standard deviation? What kind of distribution am I going to be getting? So this is going to be equal to, sigma is a constant, so I can take out the sigma, so it will be 1 over sigma. Then we will have an expectation of X minus mu. Applying the expectation algebra, this is going to be the expectation of X minus away the constant, which is mu. Expectation of X by itself, it is also mu. So mu minus mu, this is equal to 0, which means that as long as you take X minus mu divided by its own standard deviation, the expectation, the resultant expectation is always going to be equal to 0. And when you do this, 1 over sigma is a constant, so if I were to take out the variance, it's going to be 1 over sigma square, and we will have a variance of X minus mu. So 1 over sigma square is going to be 1 over sigma square, and variance of this is going to be variance of X. And what is the variance of X? Variance of X is actually also this sigma square. Cancel, this is equal to 1, which means that this is going to be 1 all the time. As long as you take X, which follows a normal distribution, minus its own mean divided by its own standard deviation, it will always follow a nice normal distribution where the parameter is always known. It will always be 0, 1, regardless of what is mu, regardless of what is sigma square. That is why we call this a standard normal distribution, one that will always follow a normal distribution of 0, 1. Just like this notation here that I was saying, this notation represents this. It is already pre-communicated by the examiner, so you can use this notation. The danger of using this notation is when you use the notation and you didn't know that it is equal to this. That's why I was saying that you must go and do the derivation, learn how to derive this, learn how to derive binomial distribution formula. For standardization, so far although I do want to recommend that you can go and memorize this, but this is not very, very useful for the exam. So it really depends on your interest. But I know that if I can just take this minus its own mean minus its own standard deviation, in the exam I can probably just write down this as Z, because this can be represented by the notation Z. So Z will be bigger than 9.8 minus mu divided by sigma. This is equal to 0.1. I can press into my calculator to do an inverse norm to find out what is this thing here. So pressing into my calculator, minus mu divided by sigma. From my calculator, this is equal to 1.2815 to my 16. So it is going to be this. So it's going to get me my first equation. My first equation is mu plus 1.2816. Sigma is equal to 9.8. This is my equation number 1. Because it is very, very simple, this first part is very standard and very simple, I am going to skip part of the question. Let me just show you the solution directly, okay? We'll do the same thing for this. And again, please, although I don't expect you guys to be doing this paper because I've mentioned that I don't need you to do this, okay? In fact, I'm hoping that you are joining me in this session to do this together with me. So, but in case some of you have already done fine, okay, but this is like really very, very simple. So this, which is what I've written down here, okay, doing a standardization, I have Z to be bigger than this, blah, blah, blah. I've gotten my second equation, press into my calculator to get this. And one very important thing that you can see from this question number 5, part 1, is how easy it is. As compared to the pure math first question, it looks like an inequality question, but it is very difficult to start the inequality question. And that is why I am really asking you guys to remember, and please remember, just start with your statistics first. Even if it is more difficult statistics than usual, you will still most likely be getting more marks as compared to you starting with the pure math first. Part 2 is also very simple. Part 2, I want to find the maximum possible value of k such that there's a chance of at least 10% that the mean rainfall chosen out of 30 days. So we are looking at another scenario after I've solved for mu and I've solved for sigma. Okay, if you were to look at this question, I just want to clarify one style of answering question with you. Okay, if you were to look at this question, it says that show that sigma is equal to 2.01. And through doing this question, you will definitely have solved for mu and you will solve for sigma. So let me write down mu. Mu is equal to 7.2278. The question didn't ask for mu. Sigma here, this is equal to 2.0071. The question asked for sigma. And the question asked us to prove that sigma is approximately 2.01 to 2 decimal places. So this is 2.01. 2 decimal places, so shown. Okay, it is in the next step that I want you to be very clear what kind of numbers you can use. This is really just for getting marks in the exam. So hear me carefully, okay? In the next part 2. Part 2, we need to build for ourselves another sample mean distribution. This time it is going to be for 30 days instead of for 7 days. So for the next part, it is going to follow a normal distribution because x is already described to me by the question that it follows a normal distribution. Its mean, now I know, so I'm going to use 7.2278. Its variance is going to be this or this square. Which one should you use? It is very, very important that you use intermediate values up to with a minimum of 5 significant figures. This we have talked about it before a lot of times. Minimum 5 significant figures. But if a question asks you to show, for example, like for the first part, they ask you to show that it is 2.01, then you actually have an option. Okay, if not, please, you must use this. You cannot use 7.23. For here, you can either go for 2.01 square divided by 30, or it will be totally fine if you were to go for this version. So for this particular kind of show, where they give you one of the numbers, you can use either or. My personal preference is to use this. But this is really just my personal preference because I just want more accuracy. But I know for Cambridge preference, they actually prefer this a little bit more, but they are acceptable to this also. Okay, I don't think Cambridge prefer this a bit more, okay, but I think some tutors, some schools prefer this a bit more because this was already given to you by the question. So it is totally okay for this case to use 2 decimal places because it is the number that you are supposed to show. But if you are scared, just use this. This will be confirmed correct. And the question says that the probability that x bar is bigger than k, this is going to be at least 0.1. And we are supposed to solve for k. And like what I've mentioned in the last session, this is the kind of inverse norm that you cannot do on your calculator because your calculator cannot handle an inequality sign here. Your calculator can only handle equal to, that's all. So we need to do an improvisation. Please make sure that you know and make sure that you have learned properly how to do this improvisation. Let's do another round of quick recap of what should we do if I'm supposed to do an inverse norm where this is not an equal to. So what I can do as an improvisation is I will always reference it to my graph. There are 2 ways for us to process normal distribution probability. And you must always alternate between these 2 ways. Because in the last few weeks, when some of you asked me a question on normal distribution, the reason why you are stuck was because you were depending only on your calculator and maybe some numerical calculation. But you have forgotten that you can always jump to the graph to analyze it. When you are working on the non-graph, you depend very, very heavily on calculations and what the calculator can give you. But the moment when you jump to your graph, your dependence is on the geometry. So you try to focus on the geometry as much as possible. My graph is going to be something that is like this. My graph will have a center here. The center here is this 7.2278. So this is bigger than bigger or equal to 0.1, which I cannot press into my calculator, but I'm going to still mark out a region that has an area of 0.1. I will press this into my calculator to get this number here, because my calculator can get me this number, right? If this number is A, probability that X bar is bigger than A, I just need to let it be equal to 0.1, then I can press into my calculator inverse norm to get A. So if I were to press this to my calculator, this A here is equal to 7.6981. This is from my calculator. And then I look back at my scenario. If the area that is on the right hand side geometrically, okay, because I'm trying to reference to here. So if the area that is on the right hand side of K is a number that is bigger or equal to 0.1, where do you think K should lie? K should be lying either to the left hand side of 7.6981 or on 7.6981, correct? Which means that based on this, I can see that K is less than or equal to 7.6981. Do you have any question? This is very, very important. Do you have any question? And what you need to do is to practice enough so that this will not slow you down. You can consider drawing, or if you can, or it will be even better if you can try to execute this without drawing. Because usually if it is not explained to you, I don't really draw this, because you can imagine this in your head. It's very easy to imagine, provided that you have been exercising that imagination. So for some of you, I think that should be your ultimate goal, to be able to do this very, very accurately without even having to draw this out. Just imagine in your head can really. But if you realize there's that inconsistency, please just draw, okay? It's better to get it correct. Okay, then if you were to look at Hua Chong's solution, okay, let me show you, okay? Hua Chong is doing this more and more often. Last time, they don't really do this, if I remember correctly. If you were to look at Hua Chong's solution, because the question asks you what is the maximum. The question asks you, can you find the maximum value of K? So K is equal to something. Find the maximum possible value of K. So for this, okay, Hua Chong wrote the answer as 7.6 to 1 decimal place. 1 decimal place is asked by the question. So Hua Chong say that the maximum possible K is 7.6. Some of your school will actually go for maximum possible K to be equal to 1 decimal place, 7.7. Some schools will actually go for this. That means they will accept this as the correct answer. Which one is safer? I feel that this one is safer. Why is this? Why is there this difference? Because this maximum K is a rounding off. This is a purposeful rounding down. Okay, this is a rounding off, this is a rounding down. Why did Hua Chong here round down? Because if you were to look at this inequality and you are going to be expressing it to 1 decimal place, this is a requirement that is asked by the question. So the question wants just 1 decimal place, a maximum K that is of just 1 decimal place. And if K is a number that is less than 7.69 something, which means that that number must be less than or equal to 7.69 something, right? So if you were to round down, then it has to be 7.6. The maximum possible 1 decimal place that is possible within this set of value is 7.6, not 7.7. 7.7 is out of the range already, because K is supposed to be less than or equal to this number, and you're quoting a number that is bigger than this number. But some schools, they don't mind. That means they don't, I think it's in general, okay, that this in A level, rounding off is, unless the question specifically says so, so rounding off is generally accepted. So you don't care that much. even if it is in an inequality. I don't know about your school. Okay, it is a bit divided. Some schools go for this, some schools go for this. But the one that is the most theoretically correct is this. So my suggestion is, if you can, regardless of your school, whether they choose this or this, if you can just process this very quickly, then go for this. Any question? Okay. Then next is a correlation linear regression question. I'm going to skip this question. We will come back to correlation linear regression to discuss it again. Too bad, okay, you guys are not tested mid-year, tested correlation linear regression for mid-year. It is like so easy to get marks. Let's go for question number 7. Which means, right, if the student has gone for statistics first in 2019, a Hwa Chong student has gone for statistics first. Question number 5 was an easy question. A little bit of tricks here and there, but I don't think it's major. Or at least when a student go through the question, the student will not feel the mistake, which is more comforting. And then question number 6 is a correlation linear regression question, which is also not a difficult question. So you tend to get warm up faster. Like mentally, I was telling you, when we talk about warm up, it is not how fast your hand is writing, okay? It is how fast your brain is processing. Your hand must still be writing at a super fast speed. Question number 7 is also going to be a pretty easy and manageable question. I'm going to try to do this question also. We will try to warm up to this question. We'll try to warm up to statistics via this question. And just in case any one of you have not started statistics because somehow you feel that your statistics is pretty okay, when you're doing your tutorial and stuff, please don't take it for granted. Because most likely for those students who feel so, like their statistics has been okay, so during June holiday, they are going to just work on their pure math, they will usually fail their statistics for mid-year. So far, okay, I've seen almost all students experience that because they are too comfortable with statistics. And the problem with statistics is not about writing. The problem with statistics is usually about reading. It's because they are always going to be giving you those kind of real-life scenario situation, and you are supposed to do the interpretation. That's why reading is usually going to be a problem. Even if you don't have time to do statistics, it is better that you continue to read. Read statistics, look at the answer. Look at the solution, then press your calculator. Usually this will make students warm up enough. You will not get them an A unless they practice, but you at least not fail. Those students who plan to do statistics, just the night before, then after that, next day go and try statistics, right? Most likely you are going to fail. So we are looking at sandwiches that is foot long, 6 inch. So for foot long, I'm going to write down my version here, okay? So for the foot long sandwich, I'm going to go for, what did I go for? I'll go for X. And according to the question, it is given to me that it follows a normal distribution. So this is going to be 12.2, 0.04. I probably should write down a proper statement to define X. Not probably, I must write down a proper statement to define X, or else I'm going to be losing marks in exam. And we are looking at a 6 inch sandwiches. This is going to, I'm going to let it be Y. According to the question, you also follow a normal distribution of this. Part 1 is super easy. For a randomly chosen foot long, it is likely to be less than 12 inches. And then compared to a randomly chosen 6 inch to be less likely, to be less than 6 inches, then which one is more likely? Which one is more likely? So we are talking about foot long to be less than 12 inches. So I'm going to calculate the probability that X is less than 12. And I'm going to calculate the probability that Y is less than 6. Which one is more likely? Is it more likely for the foot long to be less than 12, or is it more likely for the 6 inch to be less than 6? If you were to look at this statement is a randomly chosen foot long loaf more likely to be less than 12? Is it? Or when you look at this statement, you can understand what I'm trying to say. The challenge is like, wow, because it's too English. It's not difficult to hear this or to read this, but to just translate it to math, it is not like an instant thing, which is what we have been training to do through our tutorial and through our revision package. So pausing this and then suddenly requiring us to do this again sometimes can be a little bit taxing. Anyway, this I'm going to just press in the calculator. This I'm going to be getting a 0.158666. This I'm going to be getting a 0.23975. So looking at this, I can tell that the probability of x is less than 12 is less than the probability that y is less than 6. So which one is more likely? This one is more likely. It is more likely for a 6-inch loaf to be less than 6 inches than for a foot-long loaf to be less than 12 inches. Part 2. Find the probability that two randomly chosen 6-inch loaves have a total length of more than one randomly chosen foot-long loaf. So 6-inch, the total of two randomly chosen 6-inch is more than 1 foot long. So we are talking about x1 plus x2 to be bigger than wrong. 6-inch is y. So we are talking about y1 plus y2. The total length of two 6-inch is more than the length of 1 foot long. So we are going to be taking this minus away x. And like what I was telling you, please don't just lump everything together into your final, because your aim here is to come up with this, right? This plus this minus x. This should follow some kind of normal distribution, provided that x and y are normal distribution, which they are, provided that they are independent of each other, which it must because of the limitation of our syllabus. When we try to combine them together this way, they must be independent of each other. Somehow this question didn't actually talk about it. They could have asked a part, and then they could have inserted a part that asks you, hey, what kind of assumption do you think you should make in order for you to do something that is like part 2? So I was trying to tell you, please don't lump all the calculation into one step. Try to break them up into small little parts so that marks can be awarded part by part for statistics. There's no advantage to put everything together other than saving some paper. And the worst is now you don't even save paper because the amount of space that is given to you is already fixed. So this is going to be 2 times of the expectation of y minus away the expectation of x. I'm going to leave it to you to go and submit the numbers. This is equal to 0. Then we want to find out what is the variance. Variance of y1 plus y2 minus x. This is going to be 2 times the variance of y, then plus variance of x. And this, if you were to calculate it, this is equal to 0.08, which means that we are looking at this as normal distribution of 0 and a variance of 0.08. We are supposed to calculate for the probability. We are supposed to calculate the probability that y1 plus y2 is supposed to be bigger than x. That's what the question says. So like what we have already planned, I am going to bring all this over to the left-hand side. So this minus x, this is bigger than 0. I can either press this into my calculator, or I can also try to read the probability by referencing it again via geometry on my bell curve. Because I know the center here is 0 and the area that is on the right hand side of 0, this area is going to be equal to 1 over 2. So you can press it on the calculator, it should give you 0.5000 something or 0.49 something. This is going to be equal to half. Okay, it is still pretty easy. So far question number 5 was easy. 6 is, let's just assume that it is easy. 7 is also still pretty manageable. 7 part 3. Let's see whether it is still going to be as manageable. 7 part 3, Sue buys a 6-inch sandwich 3 times a week. Find the probability that Sue gets at most one sandwich that is less than 6 inches in length in a randomly chosen week. What can we do to this? Why not we try to apply a binomial distribution? Because we are looking at the number of trials as 3. The probability of a 6-inch sandwich to be less than 6 inches, we have already calculated it. It is 0.23975. And the probability remains the same for any randomly chosen sandwich. And although the question didn't say, but from part 2, we have already assumed that they are independent of each other. So all this tells me that, hey, it is a binomial distribution scenario. And I was telling you, binomial distribution is either you try to recognize it, or else you have to calculate it from scratch. If you were to look at Hwa Chong's solution, they actually gave two solutions. One is they use a binomial distribution. The other one is they calculated it from scratch. Why then should we have the motivation to try to recognize it? Why not I just calculate from scratch? Because like that, I don't have to risk spotting the binomial distribution wrongly. It depends. It depends on the question. If you were to look at this part 3, the motivation is lower. Because if I were to spot this as a binomial distribution, this is what I'm going to be writing down, okay? If A represents the number of 6-inch sandwich that is less than, the 6-inch sandwich that is less than 6 inches. So if A represents that for the 3 loaves that is bought, then this will be 0.23975. And the question is asking me to find the probability that A is less than or equal to 1. I can actually already simply press this into the calculator. This is equal to 0.855, 855, yeah, 0.855. So very, very fast, we have gotten our answer. If you were to look at Hwa Chong's solution where they gave an alternative, the alternative is here. So Hwa Chong gave an alternative, and this is actually manageable. That means if you missed spotting it as a binomial distribution, you should still be able to get it correct. So do we have the motivation to spot the binomial distribution if this is the only way when a binomial distribution scenario appears in our exam? We have no such motivation, right? So far, we have no such motivation because the calculation is still manageable. The reason why we want to spot it is number one, we don't have to go through the tree diagram, then after that, deduce a solution. Number two, the reason why we want to spot it is so that we can use the calculator. These are the two main reasons. I don't have to deduce, I can immediately use the calculator. But the process of deduction is actually still going, it has still been processed by your head, or else you cannot spot that it's a binomial distribution. So the motivation to want to know that that particular scenario is a binomial distribution is when the number gets too big. That's the thing. Which is non-existent during my time. During my time, we don't have our GC with us. So every time when it is a binomial distribution, I will still have to calculate from scratch. So I don't really see the necessity to spot that it's a binomial distribution, other than the fact that the question will require you to write down that statement that you have spotted it. Okay, but if you were to do the next question, where the numbers get bigger, in the next question, we are going to be dealing with 12 as the sample size, as the number of trials. We are going to be dealing with 9 as the number of trials. So if probability that x is equal to something doesn't scare you, then probability that x is less than or equal to, for example, 10, I believe it is going to scare you, right? Because if x is less than or equal to 10, and I cannot press my calculator, then you have to write down so many different versions, because less than equal to 10 means x equal to 10, x equal to 9, x equal to 8. You got to write all the way until 0, and you could plus them up using your calculator, your non-graphing scientific calculator. Then it is going to be a waste of time. That is why it is very, very crucial for us to want to train ourselves to spot a binomial distribution when it is there, so that we can have the kind of efficiency for the style of the question that is going to be asked nowadays. During my time, we will not be asked to calculate the probability that x is less than or equal to 10, because it's unfair. But now you guys will, because most people will be able to spot the binomial distribution. So how do we increase the chances of us spotting a binomial distribution? Like what I tried to practice with you guys last week. You learn how to do the derivation independently, without people telling you, without referring to the video. You try to do the derivation yourself independently. And we are seeing that requirement in part 4. In part 4, given that Sue gets more than 4 sandwiches, given that Sue gets more than 4 sandwiches that are less than 6 inches in length in a randomly chosen 4 weeks. Please remember, Sue is still going to be buying 3 sandwiches a week, which means that in 4 weeks, Sue will be looking at 12 sandwiches. And we're still looking at for a 6-inch sandwich to be less than 6 inches. So I'm going to create for myself another distribution to represent 4 weeks. So for these 4 weeks, it will follow a binomial distribution. 3 times 4 is 12, and the probability of success is still going to be for a 6-inch sandwich to be less than 6 inches. So it will be this, 9, 7, 5. Given that this happened, I want to find the probability that she gets exactly 1 such sandwich in the first week. So this is a conditional probability. This is a conditional probability. The condition that is given to you is that Sue is going to get more than 4 such sandwiches in 4 weeks. The probability that we are supposed to find is for Sue to be getting exactly 1 such sandwich in the first week. So we are looking at conditional probability where A is equal to 1. A is for the first week, so she will get exactly 1 such sandwich in a week. Probability that A is equal to 1. Given that in 4 weeks, she must get more than 4 such sandwich. Conditional probability. So in the numerator, it is when the first week, Sue is going to be getting 1. In total of 4 weeks, Sue is going to be getting more than 4. That means in the numerator, we are going to calculate the probability that first week, Sue is going to be getting exactly 1 only. And then for the next 3 weeks, okay, 3 weeks, we need another distribution here. So another distribution, I'm going to go for C. C is going to be representing 3 weeks, 1 week, 3 loaves. 3 weeks is going to be 3 times 3, it is going to be 9 loaves. This will be this 0.23975. So for the next 3 weeks, she must be getting more than 3. Correct? She must be getting more than 3 in order for the total in 4 weeks to be more than 4. Divided by the probability that B is more than 4. This is my conditional probability. So anyway, I'm going to leave it to you to go and calculate your probability. For the numerator, I'm going to calculate the probability by pressing the calculator binomial distribution. So now I'm starting to have the motivation because there are a lot of numbers to calculate if I cannot trigger the function that is in my calculator. For this, I will go for 1 minus probability. C must be equal to bigger than 3, so C must be equal to 4, 5, 6, and so on. So I'm going to calculate the probability where C is less than or equal to 3. Divided by, here, B is 5, 6, 7, and so on. So it's 1 minus probability that B is less than or equal to 4. And I'm not sure about this, okay, but this is just something that I see in the past few students that I have. Once in a while in an exam, you are going to see people writing down this wrongly. You know, like for example, they may miswrite this as probability that C is less than or equal to 4, or they may miswrite this as probability that C is less than or equal to 2. The same for this. So to reduce your chances of making this kind of careless mistake, if you happen to be one that is so, even if you don't know whether you'll be so, try to ask yourself this. When we were doing our binomial distribution together, I was telling you, you just recite to yourself what are the numbers that you want. Here, I want C to be equal to 4, 5, 6, 7, all the way until 9. So if I want 4 all the way until 9, I should minus less than or equal to 3 so that I can get 4 all the way until 9. So this is wrong, this is wrong. If I want to get B to be bigger than 4, that means B should be equal to 5, 6, 7, and so on. B should be 5, 6. I mean, it can just very quickly go through my head. It saves me so many marks. So please find different ways that you can for yourself. Customize it for yourself, okay? To prevent yourself from making super careless mistakes that are like this. Because if I know that it is 5, 6, 7, 8 that I want, I will minus less than or equal to 4. Because for a lot of people, during their first major exam of statistics where it is going to be 60 marks, section B is 60 marks. a lot of people can actually get 40 plus to 50. I think 43 is already going to be a B. So a lot of people can get 40 plus. But in the end, so a lot of people can get 40 plus, some will actually be able to get 50, 50 plus. Okay, but in the end, right, you realize that there are a few who are actually supposed to be getting 40 plus, 50 plus, who fail statistics. It's because of all these small little careless mistakes here and there. So when you are practicing for your statistics, you cannot just practice to press here and there. You must practice to identify different places where you can potentially make mistake, and then ask yourself, how can you reduce the chances of them happening during your exam when you're trying to rush for time. And especially we are trying to adopt the strategy to do statistics first. We are yet to be that warm up yet, which means that if you're not that warm up, you may make even more careless mistakes. Okay, so if you can just warn yourself, you can just have a little bit of strategies here and there, customize it for yourself, because you can see how you make mistakes. I can't. Only you will know where you're going to be making mistakes here and there. Any question? Question number 7. Let's take a look at 8. And 8 is what I want to discuss with you a bit more. And I'm going to be pausing 8 for a little while later to go to that worksheet that I'm sharing with you, okay? Just so that I know my audience, has anyone actually done the Hwa Chong paper 2 section B already? Anyone has already done it, or you guys are reading it together with me and then trying to solve it as I solve it? Okay. No one has replied me, so I'm assuming that all of you have not done this. No one had, right? Okay, good, because that's the ideal. I want to discuss the question from scratch together with you. So, question number 8. Question number 8, we have parallel. And we are supposed to be arranging parallel. And the problem with parallel is actually the identical objects. So I'm going to try to spot the identical objects as quickly as possible. I'm going to use the same presentation that a lot of your schools are using. I think that is perfect. I don't think I will want to even change it. So parallel, P-A-R-A, parallel. Sorry. You know, that's the weird thing about doing this part of this kind of P&C question. Is suddenly you don't know how to spell. So anyway, parallel, L-L-E-L. Okay, so at a glance, I know that there are going to be 2 A's, there are going to be 3 L's. Later, the question will be talking about vowels and consonants. So vowels, there are going to be 3 vowels, A, A, E, and the rest 5 other letters, they are the consonants. A part 1. If I want to arrange this and there were to be no restrictions, okay, no restrictions. I have 1, 2, 3, 4, 5, 6, 7, 8 letters. So it's going to be 8 factorial divided by 2 factorial, 3 factorial. No restrictions. This is giving me a 3360. How many marks? They're giving me just 1 mark. They see this as a very, very easy question. Part 2. Part 2, no L are next to any other L's. That means we want to make sure that the L's are separated. There's already an existing strategy, the slotting method. Please make use of the slotting method as much as possible. So we want L to be all separated. So we are going to arrange P, A, R, E first. 1, 2, 3, 4, 5. We are doing a 5 factorial divided by 2 factorial because of the 2 A's. And for L, I'm going to be slotting them into these positions instead of, including the 2 N positions. So we have 6 of them. So it's going to be out of 6, I will choose 3. Not super necessary, it really depends on your perspective. You don't really need to arrange the L, but if you are planning to arrange the L, it is going to be 3 factorial divided by 3 factorial anyway. So if you can really see that it is not necessary for you to arrange them, then might as well just write it down as 5 factorial divided by 2 factorial. Then 6 choose 3, full stop. And this gives me 1, 2, 0, 0. And then part 3. Part 3. We are supposed to arrange these letters, all these letters, such that the first one is a consonant, the last one is also a consonant, and all the vowels are supposed to be arranged together. So the first letter and the last letter, they must be consonants. They must be consonants. In between, there are going to be 6 other letters, and the vowels are supposed to be arranged together. The vowels are supposed to be arranged together. So the A, E, the 3 vowels. So vowels, vowels, vowels. They're supposed to be arranged together, which means that there will be there will still be 3 consonants. Let me draw this a bit further away. There will be still 3 other consonants. Okay, because you guys are doing this for the very first time, you get the scenario. The first one is going to be a consonant. The last one is going to be a consonant. And then you want to make sure that the vowels are always going to be arranged together. Okay, I'm going to show you Hua Zhong's solution. If you have the PDF with you, just look at your own PDF, it's also fine. I'm going to just flash a solution on the board. And because you guys have not really seen the question before, what I want you to do next, I'm going to have a more in-depth discussion with you, okay? So not to worry if whatever that you experience looking at their solution, but I just want you to spend some time looking at their solution. Okay, I don't want to give you too much time, okay? I want to discuss more about this together with you. So, but I don't think it is very easy for us to very quickly read this. So can I give you 5 minutes? Okay, 5 minutes. Then can you try to read this as quickly as possible and try to get it? Okay, try to get their solution. But don't ask me any question, okay? Don't ask me any question. Just read it and try to get it. Okay, 5 minutes. Can you try? Okay, can I just assume that you guys have either finished reading and you get whatever that they are saying, or you are trying, but you're also tempted to give up. Or maybe some of you have already gone toilet, come back with a drink, with your lunch or whatever, and you've already given up. But the 2 solutions, right, they are just not the kind of, I mean, yeah, they get the answer. The answer is 240, okay? Both the solution gets the answer. But the problem is, like what I was telling you, when you are doing your revision, it is going to be very short-sighted if you plan your... I mean, we cannot do this all the time, okay? But we should always try to ask ourselves, how can I use this question that I'm doing to better myself so that I can repeat the entire experience again during the exam? Yeah, if I can't repeat, then why am I even doing this? Of course, there's a purpose, okay? Sometimes when you're doing this, it doesn't help you in specifically this question, but it builds you up in terms of your cognitive muscles, then that helps you to process better. Of course, this happen. It's just that, like for example, this method number 2, with these 3 cases here, right? Personally, I feel that I will not do this again during the exam. I can say that from a student's point of view. I can also say this from a teacher's point of view. For example, right, if a student were to come to me with this particular question, part 3, and the student presented to me this, case 1, case 2, case 3. Case 1, case 2, case 3. And the worst is the student didn't manage to get it correct. And the student asked me, can you explain to me why I didn't get it correct? You know how difficult that is? And that is why teachers P&C get stronger and stronger and stronger. Not because they keep doing the correct question, It's they keep trying to answer students' questions that are wrong, and they are forced by their principals that they need to answer the question, or forced by the math department that they need to answer the student's question. So the teachers sort of like look at the numbers and then try to imagine and decipher and decode, whatever the student is thinking about, because the student has formulated their own scenario, not the questions one, but the student's own scenario. So it is very, very difficult, for even when you're presented this solution, it's already very difficult to understand, right? And how are you going to even do this again during the exam? Sometimes it is unavoidable because there are indeed questions for P and C for certain other topics where the solutions are very, very specific to that question, and you're just supposed to improvise and think about strategies all you can for that question. It is still going to be a good exercise. But now I want to talk about repeatability. And in February, March, when we were recapping probability and P and C, then I brought forth the idea of identical object. And I was trying to say that the idea of identical object can actually be a very sharp tool, but so many people abuse it. They don't know how to use the idea of identical objects properly. So let's try to recap that again. I'm going to talk about the idea once more. Okay, let me talk about the idea once more. Then, after that, we will look at this practice here, okay, which is extracted from the questions that we did in our practice exercise in I think February March period. So this you actually have, okay, it's just I extract out those questions that we discussed. So first of all, identical objects. Let me go back to my outline, okay? Identical objects. We want to see very clearly how I can understand identical object so that I can repeatedly use identical object to solve problems that are like this. My solution, or if some of you can remember what we discussed in March, my solution to this is just one step. And it's very, very clear and easy step that you can repeat on. It's very, very easy to repeat. So let us try to take a look at identical objects. P and C. Identical objects. So the idea is, when they are identical objects, I'm going to divide by identical object factorial. It's not so simple. That's what a lot of people saw when they are applying. But in March, we were discussing that there are conditions before I can apply this, before I can divide by this 2 factorial, 3 factorial, before I can do this. Let me just do a very quick recap with you how the idea comes about. And according to how we have discussed our P and C, we stack. We stack one idea to another idea, stack one idea to another idea. And the four fundamental ideas that we were trying to discuss, and everything else actually stack on these 4 fundamental ideas. One of them is identical object, the other one is permutation. Of course, there's combination, and the other one is circular permutation. We are stacking one on top of another. Identical object and circular permutation is already stacking on top of permutation and combination. Last week, we discussed about circular permutation. How did we form our circular permutation? We stack something on top of permutation in a line. So from a line permutation, we apply the line permutation, then we improve upon it to customize it for circular permutation. So circular permutation is not started from scratch. It is based on line permutation. The same goes for identical objects. If I have 3 distinct objects, for example, A, B, C, how many ways can I arrange A, B, C? If I were to use permutation, if I were to use permutation, this is 3 factorial. This gives me a 6. This is extremely fast. What is another way that I can count the number of identical objects? It's like count the number of ways that I can arrange A, B, C. I will list down the different cases. So let me try to list down A, B, C manually, and let's see whether we will get 6 different ways of arranging them. So they will be A, B, C. It can be A, C, B. It can be B, A, C. It can be C, A, B. It can also be B, C, A, C, B, A. So we have 1, 2, 3, 4, 5, 6. We have 1, 2, 3, 4, 5, 6. We have 6 different ways to arrange A, B, C. It's synchronized to our permutation calculation, and that is correct. And when it comes to identical objects, things change. For example, this C here becomes a B. So if I can just try to do the arrangement again, I will realize if I can just replace all the C by B, I will be getting something that is like this here. So this C becomes B, this C becomes B. So if you were to look at it, how many ways do we have right now? We have 3 ways, not 6. We have 3 ways. Okay, this is 1, this is 2, this is 3. We have 3 ways because C has become B. But just like what I did with you guys in the beginning, I purposely write this as like another color so that you can tell that, okay, if B and B, they are sort of like different. If B and B are sort of like different, then if they were to be different, these 2 B's are different. That means here I will have a 2 factorial because it is like A then arrange. So it is this case that is appearing for this case. So this 2 factorial. For this, it is like something, then A something. So if it is this case for this B, this black colored B and the blue and the red colored B, they can be swapped. So this is also this is going to be another 2 factorial. The same goes for here. Here is also going to be another 2 factorial, which means that in order for me to take into account of the 2 B's that are supposed to be that are imagined to be different, there's this extra 2 factorial that is added. But if B are the same, then I will have to remove this 2 factorial, correct? I'll have to remove this 2 factorial. So if B are different, if the 2 B's are different, then I can use a line permutation, 3 factorial. But if the 2 B's are the same, whatever that I've calculated, I need to remove 2 factorial. So I need to divide it by 2 factorial. So that gives me my 3 factorial. That gives me my 3 factorial. Then I divide it by 2 factorial. Do you get it? Do you understand? I want you to question me about this. Okay, I cannot guarantee that I'm explaining in exactly the way that every one of you can understand. But I want to understand how you don't understand. Anyone cannot understand why, if I were to use this example, why we are dividing this by 2 factorial? You can see this clearly, right? Anyone cannot? Okay, I'm assuming that those of you who are here can see this 2 factorial clearly now. But now I want you to see something else. Okay, by the way, 3 factorial divided by 2 factorial is going to give me a 3. Okay, which is going to be true, because there's supposed to be 1 way of arranging, 2 ways of arranging, and the 3rd way of arranging. But then, other than this 2 factorial, which we are so used to looking at, I want you to know what is this 3 factorial about. This 3 factorial is the one that is special. We want to make sure that we recognize the numerator before we apply that 2 factorial in the denominator. If you cannot learn how to recognize the numerator, then your 2 factorial in the denominator is not going to give you enough strength to reduce this question into just 1 line. And that is my purpose. I'm not going to do the same way as how Hwa Chong has done it. But the way Hwa Chong has done it is just very, it's a good solution. It's just very difficult for me to repeat the whole process again. So let's discuss about this 3 factorial. What is this 3 factorial? This 3 factorial is a line permutation. And in this line permutation, the 3 objects are seen as different. That's why we can have a 3 factorial permutation. Okay, I've mentioned this before also. When you do permutation and combination, there's actually a condition that people take it for granted. They didn't know that there's this condition sometimes, which is when I do permutation, we can only permutate from n distinct objects. That means if I were to apply n factorial, if I were to apply n choose r, this n here, they must all be distinct. I cannot have identical objects then I do permutation. I cannot, because it defies the definition of permutation. Actually, it is the same for combination. Combination. NCR. You know what is this n? N must be distinct objects. N must be distinct objects. Which means that if you have, for example, 4 red colored balls, they are totally identical. How many ways can I choose 3 balls from these 4 red colored balls? How many ways can I choose 3 balls from these 4 red colored balls? It will be 4 choose 3. Wrong. 4 choose 3 gives you 3. And that is unrealistic, right? I mean, I have 4 identical red colored balls. And if I were to apply 4 choose 3, I get like 4 ways to choose. There's just one way. There are 4 identical, no matter how I try, right? There's just one way that I can get 3 red color balls from 4 red color balls. So 4 choose 3 is already wrong. Why wrong? Because in order for you to apply 4 choose 3, the 4 must be from 4 distinct objects. There cannot be any one of them that are identical. So now we are trying to apply a permutation in the numerator. We are trying to apply a permutation in the numerator, which means that when I try to apply this permutation in the numerator, although I am looking at a A, B, B scenario, but when I first started my calculation by applying a 3 factorial, I am not looking at it as if it is A, B, B. Or else I couldn't have applied the 3 factorial in the numerator. That means when I apply the 3 factorial, I am seeing it as A, B1, B2. I need to see it as if it is A, B1, B2. Then I can apply 3 factorial. Then I divide it by 2 factorial. You get what I'm trying to say? You must first change your perspective to purposely see all the objects as distinct in order for you to do the permutation before you can take into account of the identical object by dividing by the identical object's factorial. Now, I'm going to see this as A1, A2, L1, L2, L3 in order for me to do part 3. So I want the first to be a consonant, the last to be a consonant. How many distinct consonants do we have? We have 1, 2, 3, 4, 5 distinct consonants. So out of 5, I'm going to choose 1 for the first consonant. Then out of 4 other consonants, I'm going to choose 1 for the last consonants. Is that okay, right? 5 choose 1, 4 choose 1. Or you can also just do a 5 choose 2 times 2 factorial. Okay, it is also okay if you were to do a 5 consonants choose 2, then multiply by 2 factorial to just interchange it between the first one and the last one. Okay, it is the same thing. Okay, so let's say this is settled. And again, why can I do this? Previously, I cannot do this, Previously, I cannot do this because I have identical objects. So I cannot apply choosing. I cannot apply permutation. But now I can. So after I've chosen this, I'm going to group this together to form one group object. And for the vowels, I will have 1, 2, 3. I have 3 distinct vowels. So I'm going to just multiply by 3 factorial for the vowels. Okay, I'm seeing them as all distinct, okay? Then I have 1 object, 2, 3, 4. So I'll multiply by 4 factorial. So far, any question? So I have satisfied the condition in order for me to apply the identical objects idea. Okay, like what I was telling you, in order for you to divide by identical objects, you need to make sure that whatever that is on top are all distinct. Because you are using numbers to manage it. You're not trying to list down the cases. So now I have arranged everything as if they are all distinct objects. Then I'm going to divide by, okay, now I take into account of the fact that actually it's not A1, A2, it is A, divided by 2 factorial, gone. It is not L1, L2, L3, it is L, L, L. So divided by 3 factorial. This immediately gives me 2, 4, 0. It's highly efficient. It is very, very repetitive. I mean, it's very easy to repeat, not repetitive. It is very easy to repeat. And I want you guys to try it. From now all the way until your prelim, you will definitely find chance to apply this. There are some schools that are doing this. Then some students don't understand this. Because the numbers just doesn't seem to work, because they can't see that, when some schools apply this as if it is very short, the reason why some students ignore it because they didn't know that they are trying to view it from another perspective. So in the end, right, a lot of people will still revert back to this. Especially if they can actually understand this, which is the disadvantage. They can understand doesn't mean that they can repeat the whole process again. Because if the next question were to come, the same old problem will arise. How are you going to do it efficiently? If If I cannot count faster, if I cannot calculate faster than I count, then there's no point for me to learn P&C at all. Because whatever that I can count, I can really do it with or without P&C. Any question? This 4 factorial here is because I have 1, 2, 3, 4 objects. Okay, C is at the first, then is at the first. So I still have 1, 2, 3, 4. 4 objects. So there's a 4 factorial. Any other question? With Timothy, who has just joined, in case this you find it very confusing, right? I'm so sorry, okay? Because we have actually tried to explain from scratch about this. So you can check out a bit. If you have a question, you can text me and ask me, okay? Like in case this is confusing you. But in case you actually, Timothy, in case you can actually see how this is applied, but you don't understand, well, that is also dangerous, okay? So you should still go and check the video about 5-10 minutes just before you join. We were doing the explanation. Okay. Okay. Let me show you another case. Please don't think that this is like super magical, okay? This is not super magical. This is just dealing with the identical objects. But you'll realize that this kind of question is not a lot. You know why this kind of question is not a lot? Because this kind of question is actually very easy, you know, when you have a proper way to deal with an identical objects. That means P&C train you 2 things. Number 1 is to train you to want to have efficiency. Number 2, in order to train you to have efficiency, they need to train you to give you restrictions so that you know about the efficiency and you know how to handle times when it is impossible to be efficient and what can you do the best of it. So you actually will have this other kind of question. Let's go back to that worksheet. Let's go back to question number 1. This kind of question is designed so that this kind of efficiency cannot happen. This kind of question is designed so that you have no way but to still list down the cases one by one. So please don't try to apply this to question number 1. What is so special about question number 1? What is so different between question number 1 and this? Question number 1, we have the word success. S-U-C-C-E-S-S. We have the word success. And in this 1, 2, 3, in these 4 letters, we are supposed to arrange, we are supposed to draw 3 letters from this, and it is going to form a 3-letter word. We are supposed to draw 3 letters from this. Yeah, this is the kind of question that prevents you from applying this. You know how they did it? They did it by giving you a scenario that is like this, but then they just asked for 3 of the letters to be arranged. Though when only 3 of the letters are arranged, not all the 7, okay? There are 7 letters here. Only 3 of the letters are arranged. That means immediately there's one condition that cannot be fulfilled. You will never know in these 3 letters which one are identical. You will never know because this strategy will not be able to tell you this. You will not know whether in these 3 letters there will be any identical objects. And identical objects is always a problem. It's always a problem because you must either list them down or you must just apply the idea of identical objects by dividing by identical objects factorial. So for this, you will do by cases. And that is the training that you are getting. Instead of doing the most efficient possible scenario, you are restricted and you are still forced to do by cases. So what is the problem? The problem is with the identical objects. So how am I going to list down the cases? I'm going to list down the cases based on the problem, which is the identical object. So it is actually not anyhow listing down. You are listing down the cases in a very systematic, organized manner. You are listing down based on identical objects. So I'm going to go for all distinct objects, all distinct, which means that I'm going to be working on just S, U, C, E that can be appearing in the 3 letters. So I'm working on just these 3, and these 3 are all distinct objects. This is the easiest possible. Because these 3 are all distinct objects, so I just need to take, these 4 are all distinct objects, so I just need to take 4 choose 3, multiply by 3 factorial. Will 4 choose 3 work? Yes, it is going to work because I'm choosing from 4 distinct objects. Then case 2. Case 2, again, my aim is to try to list down based on the problem. And the problem is with the identical objects that is going to appear in the 3 letters. So case 2, I can go for example, SS something. Did I go for SS something? Okay, I went for CC something. So I went for CC something. And in this something, I'm going to be just having a S, U, or E. S, U, E, there are 3 distinct objects, so 3 choose 1, it is possible. Then I mix it with this. And when I mix it with this, what you realize is you will do a 3 factorial divided by 2 factorial, correct? And let's question ourselves again, let's revisit, let's go back to the root of 2 factorial, which is actually not 2 factorial. The root of this is actually this 3 factorial. Because doing this 3 factorial is already strange by itself. We have a C, C, and a S or U or E. So this letter is distinct by itself. Then CC is weird, right? CC shouldn't be arranged, which means that this 3 factorial, when it is executed, you are seeing this as C1, C2, and then another letter here that is distinct, which allows us to do a 3 factorial. Then I take out the fact that the 2 C's are the same, divide it by 2 factorial. It is going to be the same for case 3. Which is going to be S, S, and in here, it is going to be U, C, or E. So we will have a 3 choose 1, again 3 factorial, divided by 2 factorial. And the final case, case 4. Case 4, we have a S, S, S. And I was telling you for cases that is like case 4, you can. But to be super direct and honest with you, it will be very foolish if we were to try to calculate the number of ways that SS, there are only 3 S's here. Okay, it would be foolish of us if we were to try to calculate and don't just write it down as 1. Which is what I told you guys, a few months ago. And I think some of you are actually suffering from this accidental foolishness. It's very easy to correct. Just tell yourself, P&C is about efficiency. So if you try to apply P&C and it gives you inefficiency, that means that question is not supposed to be done using P&C. You must recognize this. So there are people who will try to calculate using permutation, using combination, trying to see these 3 S's as distinct. I mean, how many ways can I arrange an SS as just 1 way? 1 is faster than all the calculation. Just stick to 1. Just list it down. So if you realize that, hey, it's very clear it's 1 way. It's very clear it's 2 ways. Please don't go and think of calculation. Please don't go and ask other people, hey, how do you think you should calculate this? What do you even want to know how to do it worse off? Spend your time to do something better. Or if in an exam, you realize that you are calculating, and in the midst of calculation, suddenly you saw something, and you realize that, actually this, right, if I can just think about it in my head, it is just 3 times. It's just 3 times. I mean, it's just 3 ways of it happening. And I'm trying to calculate it. But I managed to calculate and it's very fast also. Okay, but according to my calculation, there are 6 number of ways. 3 ways, 6 ways. How do you get the 3 ways? 3 ways is you saw it. 6 ways is you calculated it. In an exam, if this happened, what should you do? If I can give you a good suggestion, I will whack 3. 3 is the one that I saw. I really saw them arranged in 3 ways. The 6 is dangerous. You know why 6 is dangerous? Because 6 is executing something that is most likely done by executing something that is like this. And things that is like this, 3 factorial divided by 2 factorial, is one idea stacked on another idea. And the moment when one idea is stacked on another idea, it creates efficiency, but it reduced clarity. So you don't really know what happens, You just know that when you do this, it works. So if you calculated a 6 and you saw a 3, a lot of your friends will actually just go for 6. They just trust H2 math too much when they don't really need to trust H2 math. And they blame H2 math too much when it's actually their fault, So we suffer from this a lot. Just go for the 3. It is way, way better. Next. The cards are now placed into a bag and Tom is going to be drawing out the card one at a time. Part 1, B part 1. 4 cards are drawn without replacement. I want to find the probability that there is at least one vowels drawn. At least one vowels drawn, it can be 1 vowel drawn, 2 vowels drawn, 3 vowels drawn, 4 vowels drawn. So I have 4 cases. Or I can just take 1 minus no vowels is drawn. So we should always try to weigh according to our what we can calculate directly and what we can do as complement. I think that is a good strategy for exam in general. For probability question, for P&C question, complement can be a very useful tool to us if I were to know it can be an option. So if I were to try to list down cases, and there are quite a few cases, then I can just very quickly think about, if I were to do the complement, will it be faster? So B part 1, I will do the complement. So I'll take 1 minus if there were to be at least one vowel. So I'll take 1 minus if there were to be no vowels at all. So how many consonants are there? There's 1, 2, 3, 4, 5. So it is 5 out of 8. Then because there's no replacement, 4 out of 7. Then 3 out of 6. Then after that, 2 out of 5. This gives me my answer, 13 over 14. Part 2. Tom decides to record the letter of the card drawn on a piece of paper. If the letter on the card is a vowel, Tom will put it back and continue to draw the next one. If the letter on the card is a consonant, Tom will remove it and then continue with the subsequent draws. I want to find the probability that Tom records more consonants than vowels at the end of 3 draws. In our probability, we keep talking about tools. We keep talking about these 4 tools to reorganize the information that is given to us by the question, to try to list down all the possible outcomes, to try to use a tree diagram, Venn diagram, permutation, and combination. Please make sure that you are still thinking about these few tools, because sometimes it is really more useful to try to reorganize the information that is given to us by the question using either of this. Today we are going to relook again. I mean, we have already done it last week. Okay, I'm not going to go into the details of it. We're going to look at tree diagram, which we are going to be applying this now, and we're going to look at listing down all the possible outcomes. Listing down all the possible outcomes is there almost like all the time, regardless of whether it is in statistics or pure math. Many times we tend to see a situation where we list down all the possible outcome. So for part 2, we are going to build for ourselves a tree diagram. Vowel or consonant. Vowel wise, there are 3 vowels out of 8. So the first draw, 3 out of 8, and this is going to be 5 out of 8. If I were to follow what the question says, if it is a vowel, then it's just going to be placed back. So if it is going to be a vowel, it's going to be placed back. So this will be 3 out of 8. This will still be 5 out of 8. If it is a vowel, it is going to be placed back. So it is going to be 3 out of 8. Here will still be a 5 out of 8. If it is a consonant, it is going to be removed. If it is consonant, it is going to be removed. So I will have a 4 out of 7. And this is going to be 3 out of 7. The same for this vowel, consonant. This is going to be 4 out of 7. Here we have a 3 out of 7. Then vowel, consonant. This will still be 3 out of 7. And here it will be a 4 out of 7. Vowel, consonant. This will be 3 out of 6, and here we will have a 3 out of 6. And we want to look at the probability such that there will be more consonants than vowels. So more consonants than vowels, we will be looking at more consonants than vowels. We'll be looking at this branch. This will have more consonants than vowels. We'll be looking at this branch. This will have 2 consonants, 1 vowels. And we'll also be looking at this branch. 2 consonants, 1 vowels, and the last branch is going to be C, C, C. Okay, this is very simple. You can go and try to do the multiplication and addition yourself. Any question? Next, question number 9. Any question? And I was telling you for question number 9, a hypothesis testing question. It's very easy to misunderstand hypothesis testing. You know, if there were to be a chance next time, maybe we can revisit that. But today, let's just do this question, and I want to spend a little bit of time just checking out this part. Checking out this part B with you, something that I didn't do as much, you know, when we were doing our hypothesis testing the last round. So first of all, this is not the most familiar question. Actually, when we were doing hypothesis testing together, this is still not too bad because we did some that are like this. Okay, but by now, as you guys have done more and more hypothesis testing question, I do think that more and more of you would probably have forgotten that you can potentially be given a frequency table. And this is a frequency table. So I think this is very appropriate, you know, to take a look at it again before your mid-year. Because, right, as in like, okay, most of the hypothesis and correlation linear regression question that you guys have done will be giving you just this. They will not give you the frequency. Okay, but in an exam, right, I'm not sure why, okay, in an exam, they actually give frequency table not very, very frequently, but frequently enough, the frequency table. So for this case here, it is the frequency table. I want to try to calculate the unbiased estimate of the population mean and the unbiased estimate of the population variance. I'm going to be showing you the solution directly for this part 1. Okay, it's the same thing. It's very boring to just keep writing this part. Looking at the solution should be enough, but I just want to very quickly show you the calculator part, just in case some of you have already forgotten about it. So on your calculator, stats, edit, we need to plug in 2 things. So it is going to be 948 here. I mean, if you think you have forgotten how to handle a frequency table, you can press this together with me, okay, just to do a quick recollection, because I believe even for some of your revision package, you also don't see a frequency table. It is just going to be the number given to you, and it happens just one time. So, okay, then 952, and we have a 953, and we have a 955. So we have 1, 2, 3, 4, 5, 6, 7, okay. And the frequency of 948 happening is 9. So I have a 9, then this is 22, here we have a 36, and here we have a 6, 4, 1, 2. We are supposed to calculate the unbiased estimate of the population mean and the variance. So we'll press stats, calculate 1 variable stat. List 1 is L1. Frequency list, second L2 gives you L2. So second number 2 gives you L2. Calculate. So here we will then get our X bar, and X bar is equal to this 949.8375, and we are also going to be extracting out we'll be also extracting out our unbiased estimate of the population variance. This is equal to 1.3163 square. Okay, this is from my calculator. And I was trying to warn you guys the last time that this X here is actually very, very, to me, it is a good notation. But to our syllabus, I find that it can be a confusing notation. Confusing because there will be people who will say that, who will think that this Sx, once in a while, okay, they will think that this Sx is the unbiased estimate of the sample standard deviation. They will think that it is unbiased estimate of the sample standard deviation, but it is not. You don't do an unbiased estimate of the sample standard deviation when you actually have the sample data. We have just keyed into our L1 and L2. So the sample standard deviation is sigma x, which is 1.3 something. If there were to be some estimation, it is definitely an estimate of something that is not present. And the thing that is not present is the population variance. So the unbiased estimator here is definitely trying to estimate for the population. We key in the sample data, and the calculator gives me the sample statistics and estimate for me the population statistics. That's what the calculator is doing. Okay? Let's see how Hua Chong answered this part 1. And I need you to see this presentation, because by mid-year they will minus marks if you do not do this presentation. Find the unbiased estimate of the population mean and the variance, giving your answers correct to do decimal places. Let's look at how Hua Chong answered this. Using the GC, okay, fine. The unbiased estimate of the population mean is this, fine. The unbiased estimate of the population variance is this, fine. It seems to be okay, right? But look at the teacher's comment. If the student were to write mu is equal to this and sigma square is equal to this, annotate what they meant was minus wrong. Annotate as wrong, but do not deduct. Annotate that it is wrong, but do not deduct. This was 2019. Last year, I am not very sure, but I know, let's see. Hang on, I'm just seeing what schools from, what schools you guys are from. But some of your schools, I cannot tell you which schools you guys, which school that is, but some of your school, right, they will not annotate, they will not just annotate but do not deduct. They will annotate and they will deduct. What is wrong? You cannot just say this, okay? You must say that the population mean is approximated by x bar is 949.8375 or 3 significant figures. You cannot say s square is equal to this, or you must say that sigma square is approximately s square and it is equal to 1.3163 square. You must say something that is like this. That means you must say that this number is an approximation to the population mean. This number is an approximation to the population variance. They want to see this. And then, the next part. Write down the appropriate hypothesis to test the supervisor's belief. The supervisor believed that the amount is less than. Okay, so it's going to be a left tail test. You should define any symbols used. Okay, this one is something that I don't quite understand even until today, okay, but there's, I think about 2 or 3 years ago, suddenly all schools, just prior to that, if you can look at all the solutions, right, you will realize that no schools take care of this, okay, but suddenly about 2-3 years ago, all schools suddenly ask students, hey, you must define, and this one is the one that all schools minus marks. Okay, they minus marks. So what do they mean by define the symbols that you use? Let's see what kind of symbols they are talking about. I think it's because Cambridge Examiner give a feedback, which I cannot have access to. Okay, so if you have a chance, please just ask your teachers. It is this. Because at first when I read that, right, I thought, okay, like I saw marks being minus off. Suddenly, doing that, about 2-3 years ago, suddenly my students get marks minus off. I thought it is because they didn't define X. So in here, the question didn't talk about X. So X is the volume of the shower gel that is dispensed by the machine. So I thought it was just this. Then after that, I realized even students who define this, they also get 1 mark minus off. Then I realized it was this. They want students to define this mu. Okay, mu is denoted by the, mu is the population mean of the, they want students to define mu. And you must define mu accurately. You cannot just anyhow say, because mu is going to be used in this. Mu is equal to this, mu is equal to this. H2 and H1, they are standard, so you don't need to define them. So mu, you have to define. I'm not very sure why in this Hwa Chong solution, they went to list down the test statistics here. I have not seen this before, okay? So this one I'm not very sure, so I don't dare to give my opinion about this. Usually test statistics is not in the first part where you decide on your hypothesis. So mu, okay, because this is so easy, you don't expect this to be 2 marks, right? But this question is actually 2 marks. I think 1 mark is going to be for this, then another 1 mark is going to be for the definition. So mu, you want to be careful. You cannot say mu is the you cannot say mu is the volume of the shower gel. You will also get it wrong. You must say mu is the mean volume. Sorry, mu is the population mean volume of the shower gel. Or you can say mu is the mean. Without the word population is also fine. Usually just the word mean is the overall mean. But you must mention the word mean. They are very, very particular about this because there are a lot of students who will just quote this, but they leave out the word mean. So mu is the mean of something. Okay? So this question here, define any symbols. Usually it is mu. If you can, right? Okay, if you are going to be using the symbol sigma square, define symbol sigma square also. Usually it is these two, mu and sigma square. So I will say mu is the population mean of the volume and sigma is the population standard deviation of the volume of the gel. This should help you to secure the marks here, or at least prevent you from getting marks lost. So with the given data, find the p-value. I think this is easy. Okay, I'm not going to go through this. I assume that you guys know how to press your calculator to get the p-value. So in this case, the p-value is equal to 0.13474. Because the question asks for it, so your reply can be in terms of 3 significant figures. Okay, p-value, this one I think it should be fine. But then they ask something. This part. State what is the meaning of p-value in the context of this question. State what is the meaning of p-value. You know, most of the time what do they ask? They ask, can you state what is the meaning of level of difference, alpha percent level of significance, sorry. They will usually ask you to state the meaning of the level of significance. But here they ask you, can you state the meaning of p-value? Can I just ask you guys, this one I need you to respond to me, okay? Whose school actually define for you p-value? Because I do realize not all schools define p-value. Some schools that I know that actually define p-values in their notes will be, Thomas, I think your school define p-value in your notes, right? River Valley, did they define p-value in your notes? Yeah, okay, so Thomas says the school define p-value. For the rest of your schools, I don't really have an idea. Anybody else has p-value being defined in their school's notes? Okay, EJC also define p-value in the school's notes. Anyone else? I just want everyone to know whose school define, whose school doesn't, so that we can all learn, just learn it. Okay, because some schools, they actually don't. ACJC, as in like you guys define p-value in your school's notes. You are saying that because it defines in your school's notes, right? Okay. So ACJC also define p-value in your school's notes. Anybody else's school or anybody? Keith. Okay, interesting. Okay, Nigel also say, Keith also say that you define. But this is more than what I gather from the last few years. Because in the last few years, not that many schools define p-value in the school's notes. All schools will define the level of significance in the school's notes. Because the way that Hua Chong defines here, Brian and Timothy, did your school define p-value in your school's notes? Because I find this version very confusing. I mean, we are trying to get marks in our A-level now, okay? That's why we are trying to discuss all these things that are here. The only people who are more interested in getting marks like us right now, okay, will be interested to discuss about this. I mean, if I were to talk to my J1 students about this kind of thing, goodness, you know, they will think that it's a waste of their time. So, I find this statement here very difficult to internalize. P-value is the probability. P-value is the probability of the sample mean volume of shower gel in a bottle is as extreme as 949.84 when the mean is actually 950. Because I doubt Jason's school, EJC, define p-value. Did your school define it this way? Because I find this way very, very difficult to accept. I mean, it is true. I mean, if I spend some time to think about it, but it's just not very not a version that is repeatable enough for me. Jason, did your school try to define it this way? Or your school also use this as extreme as this? Because I know Thomas, River Valley, you don't define it this way, right? Thomas, your school define it in another way. Because I think, Thomas, your school's way of definition is easier for me to accept. Yeah, Thomas' school define it in a slightly different way. Yeah, they all mean the same thing. Let me give you my version, okay, which is what I copied from River Valley and I copied from VJC, because I find that version is easier to accept. Okay, which is the same as this, okay, but let me give you my version. Because p-value is seldom asked, so I don't really memorize it. So I'll always see I'll always see it from this perspective. If H0 is rejected, if H0 is rejected, then we will make sure that the p-value is less than, let's say I'm talking about alpha percent level of significance. It's going to be less than alpha over 100. P-value is less than alpha over 100. So this is usually how we see our first p-value. But if you can just change your perspective, we can always see alpha over 100 to be bigger than this p-value. Alpha over 100 to be bigger than this p-value. Which means that if I can it's just the same inequality, okay? Just in case I'm confusing you guys, I didn't change the inequality. It's just that I decided to write this on the left-hand side. Then this, I wrote it on the right-hand side. And if I can just throw in the numbers, right? Then it means that alpha over 100 is bigger than 0.13474. I mean, this is alpha over 100, but I can also say this is like level of significance. So the level of significance is bigger than 0.13474. So for River Valley and for VJC, for the rest of you, I'm not very sure. This is the most schools that I've collected that are defining p-value nowadays. I mean, like this year. So because alpha is bigger than this for rejection to take place. So the definition, right, is more based on alpha, which I thought is easier to replicate. That means p-value, this is p-value, okay? That means p-value represents the least alpha such that a rejection is going to take place. That's all. P-value is the least because alpha is anything that is bigger than this number, right? And this number is the p-value. So the p-value defines for me the smallest possible level of significance such that H0 is going to be rejected. You get what I'm trying to say? Thomas, I think your school is using this version. Anybody else's school is using this version? The smallest level of significance such that H0 is going to be rejected. Because I can do a calculation, then I just repeat my calculation in words. I thought this is way easier for me to repeat again during the exam. But in the actual thing that I'm supposed to write, I'll write this. Okay, I'm going to just write the whole thing for you, okay? I'll say that p-value. Okay, that means in my head, I'll go through this whole thing. Okay, and it defines for me the least level of significance. So p-value is the least level of significance, and I will not write least level of significance. I will replace level of significance by its definition, because we memorize the level of significance definition. What is the level of significance? It's the probability when you wrongly conclude that it is true when in fact it is true. That is the level of significance. So it is the least level of significance. Okay, it is the least level of significance, but I will just replace this by the definition of level of significance. So it's the least probability that that it is wrongly that the mean volume of the shower gel is wrongly concluded to be less than 950 when it is in fact 950. So for me, I find this version easier to accept, but you can just decide, okay? I mean, if your school has already defined one for you, just use your school's version. It's totally fine. It's just whether you can memorize it properly. I'm not someone who is so good in memorizing, so I always try to derive a meaning so that I can offload a bit of memorization work. So this is what I do. Okay, this calculated this, then this gives me the least level of significance, and I write down the same thing, but I replace the level of significance by the level of significance definition. And for those of your school who didn't define p-value, or you cannot really remember whether your school has defined it or not, please go and check your school's notes. And in case it's really not there, then use either one of the version. This one also is also okay. Use Hua Chong's version is also okay. But just try to memorize this, because you really don't know whether it is going to be asked in the A-levels or not. Okay, and this kind of thing that when it comes out in the A-level and you don't know how to define is very, very, very scary. Okay, it's really very, very scary, because in the A-level, you don't dare to lose marks. Then when you suddenly see this kind of definition thing and you don't know how to answer, right? It's just very, you just feel very insecure, okay? So the last part here is very simple, this part. It is concluded at alpha level of significance that the machine is indeed packing less than, so H0 is going to be rejected. So H0 is going to be rejected, that means p-value is going to be less than the level of significance. That is the last part, which is what Hua Chong did in their solution here. H0 is going to be rejected, p-value is less than level of significance. P-value that was calculated is this 0.13 something. You plug this in, alpha is going to be bigger than this times 100, which is this. So alpha is between this to 100. This 100 is something that, this 100 idea happens twice in Hua Chong's question. It's going to happen again in part B, and I missed the part B one. Okay, I'm going to do part B, okay, but this 100 is not because it is mentioned by the question. As in, like, it's not taken care of by your solution. So your solution only tells you that alpha is bigger than this. So alpha is bigger than 13.5. Okay, but the solution wouldn't tell you that alpha is less than 100. You got to put that in yourself, because alpha, which is percentage, is the level of significance. It couldn't go beyond the 100%, or else it's going to be irrelevant. It's going to be a probability that is more than 1. You don't have a probability that is more than 1. It will be limited at 100. Okay, so what it reminds us of is, in general, that whenever you work with a function, there will be a domain. So for the domain of alpha, it is 100. Okay, I don't know how to ask you to take care of this. You just got to make sure that you are aware of different domains here and there, throughout the question. But it is not easy because I will tell you where I missed it. Okay, it is in part B. I'm going to solve part B together with you. Okay, I'm not going to look at Chua-Chong's solution. I'm going to just do it from scratch. I don't super like their solution for part B anyway. So I'm going to just show you my solution, okay? I have a particular preference when it comes to solving this kind of hypothesis testing question, which is I prefer to solve it manually, because I think for some of you, you tend to solve it using a template. So for some of you, you will standardize. When it comes to this kind of question, you will standardize all the time. Okay, maybe let's read the question first. Due to a change in marketing policy, the machine is going to be recalibrated to pack smaller bottles. This time, it has a mean volume of 250. I was a bit confused by this first statement because I thought they were telling me a hypothesis test, going for a smaller bottle, but I realized it's just another product altogether, smaller bottles. Previously, it was 950 ml bottle. Now we are looking at 250 ml bottle. There's nothing to test. From 950 to 250, right, it's definitely going to be less. It's not like 950, then 949 point something, which is, you don't know whether it's less or not less. This is confirmed lesser. Okay, so nothing to test. And this time we are testing 50 bottles, and we are using the symbol Y. So another test is conducted at 1% level of significance. We want to test. The test concluded that the machine has been calibrated incorrectly. So we are looking at H0, where mu is equal to 250, H1, where mu is not equal to 250, because you are trying to test that the machine is calibrated incorrectly. The sample size that we are looking at is 50 here. Nice, because it is not mentioned to me whether the volume follows a normal distribution. So with n that is 50, I can apply the central limit theorem. Then y bar, I'm going to use the summation of y minus away 250 divided by n plus 250 thing. Y bar, I will be getting a, y bar will be getting a 249.5. And we will need the population variance in order for me to build my test statistics. But I don't have my population variance, so I'm going to do an unbiased estimate. The formula is standard. Okay, you're using the extended formula that we have in our outline. So I'm going to leave it to you to do the calculations yourself. And in the end, you're going to be getting this 1 over 49 k minus, okay, I think maybe this I should write because it's not exactly that standard. So this is going to be 1 over n minus 1. Then summation of y minus 250 square minus summation of y minus 250, the whole thing squared divided by n. So I have a 1 over 50 minus 1. So this is 49. Then y minus 250, this is k. So we have a k minus, this is going to be minus 25 square over 50. And this is how I derived at the 1 over 49 of k minus 25 over 2. This is my unbiased estimate of the population variance. I'm going to write down the test statistics. And because n in this case is large, so I can write down my test statistics, which is y bar. Y bar represents y1 plus y2 plus y3 all the way until y50 divided by 50. Y bar will follow a normal distribution with a mean of 250, the population mean. The population variance, which sadly I don't have, so I'm using the unbiased estimate, k minus 25 over 2. This divided by the sample size. And I'm doing this as an approximation via the central limit theorem. You can definitely write down the standardized form. I'm going to skip that because it's not very meaningful for me here. So what the question says is that there is enough evidence to support at 1% level of significance that it is calibrated incorrectly. So this is what I like to do, which may not be exactly what your school is doing, because some schools from here, they will immediately standardize. By default, you just standardize. Regardless of what, you just standardize. Okay, that's what some schools do. What I like to do for this kind of question, where I'm supposed to solve for unknowns, K, I'm supposed to solve for K unknowns. Sometimes this can be the unknown, sometimes this can be the unknown, sometimes this can be the unknown, once in a while this can be the unknown. So it is this kind where they tell you what is the conclusion, and you're supposed to make use of the conclusion, because in part A, you derive at the conclusion yourself, right? So those kind that gives you the conclusion and you're supposed to work backwards. I always like to draw on a bell curve. I find that is very, very clear. Okay, I prioritize clarity for this instead of the efficiency, because I believe that this clarity, although it may cost me some time in the beginning, but it improved my precision a lot, and it protects my understanding. And if I can just keep practicing a few times, this strategy can actually be done very, very fast. As fast as if you were to just blindly go through the standardization and then solve this, solve that, because you memorize the p-value. It can be as fast as that, but it needs more practice. So I like to do this. I like to draw the bell curve, and this is y bar. Some of you are already doing that, I know. Okay, then this, I have a 250. Because I'm drawing this, and we are talking about 1% level of significance, and it is a two-tailed test. So my critical region is going to be on the two sides here. So on here, we have a 0.01 divided by 2. In here, we have a 0.01 divided by 2, which is equal to 0.005. So this is equal to 0.005. A rejection has happened, which means that the evidence that I've collected, 249.5, is going to be within the critical region. I mean, I don't need to go and guess. From the number, I know it is going to be on the left-hand side. I mean, it's very weird if you were to go and put it onto the right-hand side, right? So this, I know it's going to be on the left-hand side. This is 249.5. It is definitely here. So if I were to just gauge, I know that this area here is smaller than 0.05, and that's how I'm going to form my first inequality. So the probability that y bar is less than 249.5, this is going to be a number that is less than 0.005. And I have my distribution. I have this. I can just press my inverse norm to solve for the unknown k. And before I can press inverse norm to solve for the unknown k, I believe we got to standardize this, because I cannot press this with my calculator for inverse norm. So I'm going to standardize this. I'm going to take the whole equation. I'm going to take the whole inequality minus away its own mean, divided by its own standard deviation. So this is going to be square root of 1 over 49.50 is going to be 1 over 2450. 1 over 2450 of k minus 25 over 2. This is less than 0.005. Sorry, this is 249.5 minus 250. And now I can press into my calculator for inverse norm. When I press into my calculator for inverse norm, again, I'm doing that visualization thing. I'm going to draw it here. So I am working on Z, and I know that to the left-hand side of a particular number, where this area here is going to be 0.05. Okay, the area that is on the left is equal to 0.05. So I can press into my calculator this. If I were to press into my calculator, this is equal to minus 2.5758. And since the area that is on the left-hand side of this is less than this 0.05, then I know this number here, it has to be on the left-hand side of negative 2.5758. So I know 249.5 minus 250, this divided by the square root of 1 over 2450, k minus 25 over 2. This must be less than minus 2.5758. And you manipulate this to get k. And if you have manipulated this to get k, k is supposed to be less than or equal to 104.8. 104.82. And this is the one that I've missed out. Because if you were to look at Hua Chong's solution had this. Okay, Hua Chong's solution had a 12.5. Hua Chong's solution had this. So to be super honest with you, I missed out this. I didn't put in this 12.5. So I was just thinking, where did this 12.5 come from? You know, what did I miss out? What I missed out is the fact that when it comes to the variance is where k lies, and the variance must always be positive. Variance cannot be negative. So if I were to let this 1 over 49 of k minus 25 over 2 be always positive, then k is going to be bigger than 12.5, which must be added in here. Okay, we will be doing a few more hypothesis testing questions, and I'm going to try to brainwash you guys to use my strategy, but I'm also a bit scared, okay, that along the way as I try to brainwash you to use this and you are still sticking to what some schools are doing, like for example here, like they jump from here directly to here. It means they have done some kind of memorization work, which you cannot explain the rejection or non-rejection that easily. I mean, it can still be done, provided that you think a lot. But when a student don't think that much and then they try to apply this, it can be quite dangerous. Because H2 math is trying to get us to think. It's not trying to get us to write. But this is what we must understand. So if we don't develop the style of thinking and we depend too much on the brute manual work, it's not going to work too well, okay, for us when we go to the university. And because university look out for people who think, instead of people who just keep writing. So that is why you may not get an A, or you may not get into the course that you want because you don't fulfill that kind of criteria. So anyway, I'm going to talk about this one more time, and I hope that this diagram has explained to you guys clear enough about the rejection that is happening. Do you have any question, regarding the diagram that I've just drawn? The last part is very simple. Do you need to give any assumption? No assumption is needed because n is large. Explain whether there's a need for the supervisor to say anything about the population distribution. Because n is large, so we can apply the central limit theorem. Okay, the last part is very simple. Nothing much that I want to say about the last part. I want to very quickly talk about question number 10. Is the last question, yeah. I want to quickly talk about question number 10. By the way, you will be expecting, if it is a 3-hour paper, you will be expecting about 10 to 12 questions. But 12 is not the max. 10 to 12 is just a guidance given by Cambridge for a 3-hour paper. Because I've seen schools that, I don't even know how they managed to do it, okay? They set like 15 questions, and it's not like they are shorter, It's just that the marks looks the same, but actually the questions are almost the same length. But most likely, for you guys, if you are having a 3-hour paper, it should be a 10, maybe 10, 11, 10 to 12 questions should be there. Okay, just to quicken up a little bit, I think for the last part here, right, I'm going to discuss this by flashing the solution here, okay? So can you guys take a look at the question yourself on your paper? Okay, maybe let's read the question a bit first together. Okay, since you have not you have not done this paper. So you have a 4-sided fair dice, 1, 2, 3, 4. So we have option A, option B. I want to find the expectation of the money that is won by the player in option A and in option B. For option A, the player just score according to what that appears on the dice. So for option A, it's very simple. If I were to say WA is the winning from option A, then I can create for myself a probability distribution table with lowercase w and probability that uppercase W is equal to WA. And the possible outcome will be 1, 2, 3, 4. This is the amount of money that is earned. Now, this is the amount of money that is won. It is what that is appearing on the dice. So, because this is a fair dice, so this is 1 quarter, 1 quarter, 1 quarter, 1 quarter. I personally like to do a probability distribution table for myself, or the probability distribution. Probability distribution need not be in the form of a table. So you'll realize that sometimes when a question asks for a probability distribution, they actually give you in terms of a piecewise function, or they describe to you somehow. That means as long as you can find a way to communicate all the possible events that can appear, where the sum of the probability is equal to 1, then that is the probability distribution already. So in Hua Chong's solution, expectation of WA is just 1 times this plus this times this plus this times this plus this times this. As for option B, the amount that is scored is going to be a bit more complicated. If the first score is X and the second score is Y, that is what Hua Chong did. I think this one went out a little bit, so Y should be here, okay? So Y and X. So if the score is X, first score is X and the second score is Y, if Y is bigger than X, then the player will win 2 times of X times Y. So if this is Y, this is X. If Y is more than X, for example like this, 2, 1, then the player will score 2 times of X times Y. So 2 times of 1 times 2 gives me 4. If Y is bigger than X, so it will be 2 times of 1 times 3 gives me 6. 2 times of 1 times 4 gives me 8. Similarly for this, Y is bigger than X, so 2 times of 2 is 4 times 3 is 12. If Y is less than X, then the player is going to lose X minus Y amount. If Y is less than X, for example this, Y is less than X, so the player will lose 2 minus 1 minus $1. Y is less than X, the player will lose 3 minus 1 minus $2. Okay, so this is how they have built up this grid here. And what are they doing? This was another tool that we were saying just now. Tree diagram, Venn diagram. You know, how do we calculate probabilities? Tree diagram, Venn diagram. We calculate it using PNC. We can also calculate it by listing down all the possible outcome. Last week we discussed about the power of grid and I say like grid. You know, so using a grid format is useful provided that you see for the situation that is given, the appearance of the individual outcome here has the same probability. Then this kind of listing down all the possible outcome is useful. So please take note of this again, because I don't want you to anyhow use this kind of grid. Actually, I think we have done a question before previously, okay, where I show you the grid doesn't work. That is when you try to list down. For example, it is a non-fair dice. If it is a non-fair dice, can you list down the outcome? Yes. But the outcome doesn't have the same probability. Because it is non-fair dice, so if let's say this is a non-fair dice and you realize that the surface 1 is super big, or the probability of getting 1 is super high, then you cannot say that anything that is happening here is just 1 out of 16. You know, 0 happened 1 out of 16 times, minus 1 happened 1 out of 16. That's not okay. Like if 1 has a higher chance of happening as compared to 2, 3, 4, then by listing down this grid, you know, it is not very useful, because the reason why you are listing down in terms of a grid is so that you can manually count to come up with the probability. But if one has a different probability, like higher chance of it happening, then for -3 to happen, it is not 1 out of 16. You got to calculate it separately. So it defeats the purpose of using the grid. But if you can use the grid, you should try to use the grid instead of doing all the manual counting. Because that's what a lot of people, they don't do. They try to imagine too many things in their head. Then they will ask, oh, should it be this or should I have a 2 factorial because there are 2 things happening, so should I? But the more we list it out into a grid, it becomes very, very clear. And from this grid, Hua Chong didn't do it, but we can definitely try to write down our probability distribution table. Let's say WB and probability that WB is equal to WB. So I'm going to list down all the possible outcome. All the possible outcome will be -3, -2, -1, 0, 4, 6, 8, 12, 16, 24. These are all the possible outcome. 3 happens 1 time, so it's 1 out of 16. 2 happens 2 times, 2 out of 16. -1 happens 3 times, 3 out of 16. This happens 4 times, 4 out of 16. This happened 1 time, 1 over 16, 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 and this is also 1 over 16. So the expectation of WB, it will be this times this plus this times this plus this times this. But if you look at how Hua Chong did it, right, they are very smart in terms of their solution, because they decided not to consolidate everything together to form the probability distribution table. So they try to look at it one by one. So even for 2, okay, they see it as if it is -2 happened once. So -2 times 1 over 16. Then -2 again. So that's why they have 2 minus 2. They have -1, -1, -1. They just list down every single term, then multiply by 1 over 16. Okay, this is also very, very fast. I thought it's a smart move. The expectation, which one do you think you will be expecting to earn more? Expectation of this is higher, so option B will earn more. Part 2 suggests why a risk-averse player would choose option A. I think Hua Chong gave a very commonsensical answer here. In fact, it was the question that is already requesting for a common sense to be applied. You will choose option A because for option A is sure win. You will never lose. You will definitely win something. If you were to choose B, sometimes you will lose, sometimes you will win. It's just that when you win, you can win big time. If you choose option A, the maximum you will win is $4. But option B, the maximum that you can win is $24. So, you will still expect people to be playing option B. It's just that sometimes you may lose. Part 3 show that the variance of the amount won by a player who play options A is 1.25. This is easy. Since we have already built for ourselves the probability distribution table, we can find expectation of WA squared, then apply into the formula. I'll be able to show this. In the competition part, the next part, in the competition, A and B each play the game 50 times. A choose option A and B choose option B. It is given that the variance for B, okay, we don't even need to calculate. The variance for B is given to us 887 over 16. I mean, we can definitely calculate it ourselves, but I think they don't, since they already asked you to calculate A, then for B, they just give it to you. I like this kind of question because the concept has already been tested. So testing it one more time is just very extra. So it is great that Hua Chong just gave us the variance of B directly. I want to find the distribution of the total amount that is won by Abel and Benson. Can you see this? You want to write down the distribution of the total amount won by Abel and Benson because this game is played 50 times, which means that for Abel, it is going to be WA1 plus WA2 plus WA3 all the way until WA50 in order for you to look at the total winnings, which is what Hua Chong wrote here. WA1, WA2 all the way until WA50. We are supposed to write down a probability distribution that can describe the total amount. And can you see what they wrote? I don't know how many of you saw this coming, but they have A, which is representing this, as a normal distribution. And they wrote down this normal distribution by the central limit theorem. Please don't take this for granted. I can still remember my conversation with my Hua Chong students during that year. A lot of them, they didn't expect that they are supposed to do an approximation because of the way the question is asked. They thought that, hey, if they ask this, right, then it must either be a normal distribution, which can't be because the question didn't say there's a normal distribution, but how can this be a binomial distribution? Because they only learn these two. And central limit theorem, sometimes it didn't occur to some of us because we always thought central limit theorem is applied to where n is large. Then this can be approximated to a normal distribution via the central limit theorem. It is meant for sample mean distribution, but actually it is not. Central limit theorem is applied when you put a lot of things together, that's all. When you put a lot of things together. So when you put a lot of things together, you get a normal distribution. Then when you divide by n, it will still be a normal distribution because it's just a constant multiplied by a normal distribution. So the primary application of central limit theorem is when you put a lot of things together. It is not just meant for sample mean distribution. And that is why Hua Chong is able to apply the central limit theorem to both A, where you put 50 of A's together, again to B, when you put 50 of B's together. Please take note of this. I do realize that although central limit theorem is still mainly being applied to a sample mean distribution, but there are more and more scenarios that I've seen coming out in prelim, media I'm not sure, okay, but in prelim where the schools set a question such that central limit theorem is applied to a non-sample mean distribution scenario. Okay, just out of curiosity, for those of your, for your schools, has any schools sort of like more explicitly mentioned that central limit theorem is also applicable to this instead of just to this? Any of your school actually say central limit theorem is also applied for x1 plus x2 all the way to xn, provided that n is large. You don't need to divide by n. Because most schools will, all schools will talk about, when x1 plus x2 all the way to xn divided by n. But any of your school try to talk about central limit theorem without having the divided by n portion. That means it is just this. Any of the schools talk about this? I know one school talked about this, which is NYJC, but none of you are from NYJC. Anybody's schools actually talk about this? Anyone's school? Okay, then because even for Hua Chong, they don't talk about this. At least for that year, I know. But then these still appear in the exam. So please take note, okay? Your school need not talk about this in order for this part to appear in the exam. And the last part is very simple. It's just A minus B, form another distribution, then calculate for it by pressing into the calculator. There's nothing much to this.